Okay, so we're going to do here problem 13.12. This is on page 458. And questions about eating oat bran. I'm not going to read the entire question, but we're looking at 120 volunteers who ate oat bran for breakfast, another 120 who ate another grain cereal. Now we're computing trying to infer whether if there's a difference in cholesterol reduction between these two groups. Okay, so first thing I want to note is we have independent samples. Why are they independent? Well, it's because we're looking at these two different groups. It's not as if there's a direct link between the subjects in the first sample and the subjects in the second. So we have independent samples, which means we'll use the techniques in section 13.1. And then we're also going to need to identify the groups. We'll let the oat bran group be group 1, or sample, referred to as population 1, and the other grain as population 2. Okay. And we'll also see here that we're looking at whether the oat bran reduction or the cholesterol reduction is difference between the two. And so we're going to look at whether there's a difference in means. Okay, so again, this refers to the type of problems that we have in section 13.1. Okay. With all this in mind, let's go and start the 6 steps of our hypothesis test. And we're actually not told the significance level, but we're going to assume that we need to use a 95% significance level, or I'm sorry, a 5% significance level. Okay. Okay, so here we go. The first thing we'll look at are our assumptions. We're not going to look at those here, but again, I said we need to have unbiased samples. In other words, there can't be any bias in how we chose these volunteers. And secondly, it has to be the case that we believe at least a population distribution for each population is somewhat normal. Okay. Again, we normally look at that through the use of a histogram of the sample data, but we're not going to do that here, but that's the typical way to check that second assumption. Okay. So past those, now we'll talk about the hypotheses. And as usual, we need a null and alternative hypotheses. So first, let's talk about the null. And remember, with these comparison of means, the way we're going to do is the parameter we're going to estimate is that difference in population means. So the parameter here is mu1 minus mu2. Okay. And we're testing, is there any difference between the cholesterol reduction of the two groups? So any difference means that we're testing whether the difference is 0 or not. Okay. So our null is that the difference in population means is 0. Then our alternative hypothesis is that same parameter, bring down that value and think about what is the operator here in between. We're testing whether there's any difference between the cholesterol reduction. In other words, any difference in those population means. And so we have a not equal sign there. Okay, so that takes care of step 2. 2 things to note from this. First off is that what is our hypothesized value of the difference in population means? Well, the hypothesized value is 0. In other words, that's the value we're testing against. The other thing we can take away from this is the type of test we have. We have a alternative is simply not equal to, therefore we have a two-tailed test. So those are things we can take away from the hypothesis. So the next step we're going to look at is calculate, or at least construct our rejection region. I said for rejection region, we'll always need 2 pieces of information. First off is the type of test. And the second piece of information that we need is the significance level. Okay, so here, again, I would suggest drawing a picture. Here we know for this type of test, our sampling distribution is a t-distribution. So it's going to look somewhat like a normal distribution, starting at 0. First thing I'm going to do is apply the type of test we have. We said earlier that we have a two-tailed test. Okay, that means we have a rejection region in both tails of the distribution, so both the left-hand tail and the right-hand tail. And we know what we're trying to find here is these critical values. I'll label them critical value A, critical value B. Next thing we apply is the significance level. We were told that we're using a 5% significance level. 5% divided equally between the two tails leaves me 2.5% in each tail. 2.5%. Okay. So what we're going to do now is find out where these values are the critical value. Again, I'm looking at a t-distribution where my t-tables in terms of right tail probabilities. So I'm going to look at this critical value B first. The critical value B is going to be a t-statistic. We're told here that, or we see that we have a 2.5% right-hand tail probability, so that's 0.025. Next we have to worry about degrees of freedom. And one of the things I forgot to mention earlier is that on this test, we're going to assume that this test we're going to use the equal variance formula. So in other words, we're going to use the formulas that apply when the population variance of, or the variance of population 1 is equal to the variance of the population 2. Okay, so in this case, that formula we know from calculating the degrees of freedom, V then is equal to N1 plus N2 minus 2. Okay, so now we're going to calculate this degrees of freedom. So N1 we're told in the book, in the appendix, is 120. That's the sample size of the first sample. Sample size of the second sample is also 120. Then minus 2, that gives me 238. Okay, and for our purposes, since our table stops at 200, we'll go ahead and round up and assume that 238, we're going to treat that pretty much as infinity. Okay, and so this critical value is a t-statistic with a 0.025 right tail probability and infinity degrees of freedom. And if we look at our table, look at column for 0.025, infinity degrees of freedom, we see that value is 1.96. Okay, so that critical value in the right tail is 1.96. The left tail, we know, since this distribution is symmetric, this is going to be the same value with an opposite sign. So critical value A, we can write that as t-statistic. Right tail probability there is going to be 0.975 with, again, infinity degrees of freedom. But we know by symmetry that's just going to be negative 1.96. Okay, and so our conclusion here is that our rejection region is when our test statistic, the absolute value of it, is greater than 1.96. Okay, so that concludes the third step. We now know what values of the test statistic will lead us to reject the null hypothesis.